All right, now we're going to look at differentiability. So we want to understand when is something differentiable versus not differentiable, and what does that actually mean? Are you differentiable? Am I differentiable? I am, actually. Are you, though? That's something for you to decide. Okay, so what makes something differentiable versus not? So some things that will destroy you. I won't, actually. Sorry, that was mean. So some things that will destroy differentiability, though. A discontinuity. So a hole, break, an asymptote, those are all things where a function is not differentiable at that location. A sharp turn, or sometimes this is called a cusp, potentially. So this is, an example of this would be absolute value of x when x is 0. So there's a sharp turn there. A vertical tangent line. So when would a vertical tangent line occur? Because if a vertical tangent line occurs, doesn't that mean it's not a function? Not necessarily. So a vertical tangent line occurs in something such as the cube root of x. So right when x equals 0, at that instance, there is a vertical tangent line. So if f is differentiable at x, then f is also continuous at x. That's something important to understand. Remember, we talked about continuity in the last unit. So if it's differentiable, then it is continuous. However, the converse of this is not necessarily true. So we want to make sure we understand that. So converse is not necessarily true. What do I mean by that? I mean that continuity does not always mean that it's differentiable. And that should make sense because two of the examples we gave up here of where something is not differentiable, they are continuous functions, like absolute value of x, continuous function, not differentiable at x equals 0. Cube root of x, continuous function, not differentiable at x equals 0. Another thing I want to emphasize about this, when we're saying something is not differentiable, it does not mean that the entire function, that we can't take the derivative. I can take the derivative of the absolute value of x. Oh, I can. I can take the derivative of cube root of x. You better be darn sure about that. But the derivative is not going to be defined at x equals 0 for both of those examples. That's what we're talking about. So when we're talking about differentiability, we're talking about, it's kind of like continuity, where a function can have pieces where it is continuous, and then there might be a hole. So it's just discontinuous at that hole, but there are still areas where it is continuous. So that's what we're talking about with differentiability as well. Let's look at an example. This will make more sense. So here we have f of x equals the absolute value of x minus 4. We want to find the derivative at x equals c, or determine that it does not exist. So in this case, c is 4. Now, spoiler alert, this is an absolute value function. I know that it was shifted 4 to the right. Therefore, the turn in the function, that sharp corner, is going to be at 4. So this is not going to be differentiable, but we need to kind of see that, or see how we can show that. This is also where we want to use the alternative form of the derivative. So we need to do the limit as x goes to 4 from the left of f of x minus f of 4 over x minus 4. And I know that this is the limit as x goes to 4 from the left of the absolute value of x minus 4 minus 0 over x minus 4. Now, so the 0 is because f of 4 is 0. And then I've seen this, by I mean we, have seen this in last unit. I know what this function looks like. And so I know that the limit as x goes to 4 from the left of this function is negative 1. Now we're going to do limit as x goes to 4 from the right, and this is f of x minus f of 4 over x 4, but this is the limit as x goes to 4 from the right of the absolute value of x minus 4 minus 0 again over x minus 4. And again, from last unit, I know that this is 1. Now, I also know that because, again, what does this represent? It represents the slope of the tangent line. What is the slope of the absolute value function? It's either 1 or negative 1, depending on which side of the turn you're on. Okay, so what did I show? Well, I showed that since this has a slope of negative 1 and this has a slope of 1, just to the left and to the right of 4, I know f is not differentiable at x equals 4 which means that the graph doesn't have a tangent line at that point. And again, that should make sense because we want to think about when we're talking about drawing a tangent line, there needs to be only one unique tangent line you can draw at any given point. And if it's a sharp turn, there's more than one tangent line you could draw. Alright, I want you to try this one. So determine whether the function is differentiable at x equals 2, and determine if it's continuous at x equals 2. Pause the video, try that on your own, unpause when you're ready to check. Alright, so what did we come up with? Hopefully you came up with that the one-sided limits are equal, therefore f is differentiable at x equals 2, and since it's differentiable, I know that f is continuous at x equals 2, because remember, differentiability means continuity. Continuity doesn't necessarily mean differentiability. Okay, how do we come up with this though? Bunch of one-sided limits. Alright, so I have this piecewise function. So first I did the limit as x goes to 2 from the left. Which one of these pieces includes 2 from the left? That's this piece. So the limit as x goes to 2 from the left of f of x minus f of 2 over x minus 2 is the limit as x goes to 2 from the left of 1/2 x plus 1 minus 1/2 times 2 plus 1 over x minus 2. So I end up with the limit as x goes to 2 from the left of 1/2 times x minus 1 over x minus 2. I factored out 1/2 from both of these, and I ended up with 1/2 times x minus 2 over x minus 2. So the limit as x goes to 2 from the left of 1/2 times x minus 2 over x minus 2. Those reduce, and I get 1/2. So what does that tell me? That tells me that the slope of the tangent line at 2 for this piece is 1/2. So then I did the limit as x goes to 2 from the right of f of x minus f of 2 over x minus 2. So now I use the other piece. I get limit as x goes to 2 from the right of root 2x minus 2 over x minus 2. Multiply the numerator and denominator by the conjugate of the numerator to rationalize the numerator. Simplify. Yada yada yada, factor out 2, x minus 2 is reduced, plug in 2, and again I get 1/2. So boom. Limits are equal, therefore it is differentiable, because that means, so yeah, let's talk about what does that mean. That means that each piece has the same exact slope at x equals 2, which is crucial for differentiability, because if they don't have the same slope, then when they connect, it's going to be a sharp turn, assuming they connect. But since they have the same slope, they will connect smoothly, and they will also connect, because remember, the differentiability is telling us that they are continuous. Alright, so we need to make sure we understand when and how to use the alternative form of the derivative. And keep in mind, differentiability does mean continuity, but the converse is not necessarily true. Continuity does not mean differentiability.